In this video, we're going to take a look at a test that allows us to utilize some of our knowledge about integrals and apply that knowledge to our study of infinite series. So, we get to use one object, i.e. an integral, to tell us information about another object, i.e. a series, right? So before we get into the nuts and bolts of it, let's take a look, like maybe give you kind of a geometric way of interpreting what infinite series is. I know that sounds weird, infinite series is like an infinite summation. How could you possibly get anything geometric out of it? Well, just leave it to math. So let's take a look at well, first of all, let's kind of go back and remind ourselves about something else that involved infinity not so long ago, which was the improper integral where the upper limit was unbounded, right? So we had this improper integral, and I'm just going from 1 to infinity. It could be generalized, and let's say this is our definite integral. We know how we can interpret this geometrically, right? So I am going to make an assumption about the function. So I am going to assume that that f of x is, let's say, always positive, right? So at least always positive on this interval, right? So let's say always positive on the interval 1 to infinity. Let's say that it's continuous, right? So continuous on that same interval. Oh, that just looks like one big mess. So continuous on the interval 1 to infinity. And then let's also assume that it's decreasing, right? So decreasing. So quite a few assumptions, but in a little bit, I'm actually going to make an argument that some of these assumptions can be dropped. In other words, actually, the piece that can be dropped is the whole 1 to infinity part, right? But let's just assume for simplicity that that's the case. Well, under these assumptions, then I can associate a certain area with this improper integral. So I could draw the function. Now, if you think about it, if the function is always positive and always continuous and always decreasing, that limits, right? That limits the way I can draw it. Really, it can only look like this, right? and then so now as far as the area, so if I, let's say, mark this off as 1, then yeah, our improper integral just represents the area of this unbounded region now. And it's unbounded because there is no upper limit, right? So again, our upper limit goes off to infinity. So this is our unbounded region. Right? And what we had said was, okay, if this integral converges, and we have a procedure for figuring out how it converges, then it means that the area, the blue area, would be finite, right? So even though it goes off, the region is unbounded, that does not mean its area has to be infinite, right? Okay, so we can take the same approach and see if we can come up with a way of visualizing this other object now. It's like the object of our affection, or not so affection. But anyway, so the series, as k goes from 1 to infinity, and let's say I'm just going to use the same symbol here, f, but to indicate now that we're only going to be evaluating this function at the integers, I am going to write f of k as opposed to f of x, right? So that subtle change there is really a conceptual one. But let's assume that all of these things, these properties, still hold. So is there a way I could visualize this? Right, funny you should ask. Because there is. So what I can do, and so I'm going to mark off now the integers, right? The 1, the 2, the 3, and so forth. Now, again, because my function is always positive, so it means the what I'm going to draw is going to be just in the first quadrant here. So when I evaluate this function at k equals 1, so at our first positive integer, then I'm going to have some number. I'm just going to label it as f of 1. And it's going to, and again, remember how we talk about plotting the points on a sequence? Then it basically looks like this. It's just a dot above there, right? And then do the same thing, and I skip all my values between, all my real numbers between 1 and 2, and I evaluate my function at 2, then again, because it's decreasing, then it's going to be a little bit lower, and that will be f of 2. I'll just draw one more, and then if I evaluate it at 3, let's say it's here, and then I will end up getting like f of 3 would be about, let's say about here, right? Now, I don't really see a nice region like I do here, but I can, because one thing I can do is, even though I don't really see a product here, I can always think of it as times 1. And if you think of, like, what sort of object do you know where its area is just like the product of two numbers, right? Well, that would be like a rectangle. So if I were to draw a rectangle where, let's say, its height is the function, the term in our sequence, right? The f sub k is our height. And then if the width or length is 1, then I can associate the first term of this series with the area of that rectangle. So this is the way I will draw the rectangle. I'm going to draw it like this, and then like that. Right? And there you go. So this width, so basically I have the rectangle centered at the integer 1. The height is clearly f of 1, and the width is 1, right? And then I'm going to repeat that process for all the other function values. So for the second term, I will associate it with the area of this rectangle. And then the same thing, the third term, f of 3, will be associated with the area of this rectangle. And then it will go on. So because it's an infinite series, right? And because all the terms are positive, right? I will always have, it might be a really, really short rectangle. Or maybe we shouldn't say short, maybe we should say vertically challenged rectangle. But it will look like this. And so now, I'll use a different color here. So now I can say, well, what does the whole series represent? Well, it represents the total area bounded by these rectangles, right? By these rectangles. And again, there are infinitely many of them. They're, again, vertically challenged rectangles in the long run, right? But there's some, right? Or the sum of the series, if the series converges, what that would imply is that we would have a finite area under all these rectangles, just like in the case of the improper integral. If the improper integral converges, we have a finite amount of area under the curve. So how are these things related? Well, what if I took my curve and basically said that the height of the rectangles, that height corresponds to the points on the curve at those integers. So suppose the function values right, on my curve at the integers, just at the integers, at 1 and at 2 and at 3 and at 4, coincide with the value of the terms of my series. So then I could draw a curve passing through the midpoint of each of these rectangles, right? So then, let me kind of superimpose the areas now. So I'm going to switch over to red areas under the curve. So under the curve, I would basically have, let me go this way, that area, right? And this is by no means a formal proof, right? I'll consider maybe doing the formal proof in a separate video. It is a little lengthy. But just intuitively, if the area under the curve happens to be finite, it is reasonable, right? It is reasonable to think that the area under the rectangles will also be finite. So if the red area is finite, right, it's reasonable to think that the green area will also be finite. And similarly, if the red area is infinite, it seems plausible, right? It's within the realm of possibility that the green area is also infinite. And what that means is, if I have to determine, for instance, if an infinite series converges or diverges, what I can do under these assumptions, I can look at the corresponding improper integral and see if it converges or diverges. So it's almost like, to me, this is like coming full circle. Remember, when we started talking about area and definite integrals, we used areas of rectangles to approximate the area under a curve. But now we have all this theory and all these techniques that allow us to evaluate a lot of these types of integrals. Now we can go back the other way and say, hey, Mr. Infinite Series, now that I am, a big hot shot, I can help you out. I can you can work with me, and I will be able to tell you if you converge or diverge. So in other words, we can now use an improper integral as a way of almost estimating the infinite series. Now it should also be clear that even if there is a finite red area, that it's not going to be equal to the finite green area. Just the way I have it constructed here, you can see that it's never going to be a perfect, almost, representation of area. Like, for instance, there are some portions of the rectangle, like here and also over here, that are not under the curve. And then there are some areas that are under the curve but outside of the rectangles. So basically what we can say, and this is the last thing I'll write down before I state the theorem, but in principle what we can say is that the value of the improper integral, whatever it may be, is approximately equal to the value of the infinite series. Right? Under certain circumstances, right, we can say whatever this value is, it's going to be approximately equal to this, right? So again, it makes sense that if this is finite, right, and it has a finite value, then the series will have a value that's approximately equal to that. So it's almost like you can use one to approximate the other, right? And right now, so let me just make one comment about these assumptions here, right? These assumptions, they make it easy to kind of visualize, and some of the math works out really nicely, especially when you do that formal proof when you make these assumptions. But technically, it doesn't always, these properties don't always have to hold over the entire interval. These properties really just need to hold eventually. So like eventually, it doesn't have to start out that way, right? So maybe not from 1 to infinity, but maybe from a billion to infinity, or a billion to the 1 billionth power to infinity. Then these properties hold. In other words, um, so I'll just write this as a note. The properties of positivity, continuity, right? And let's just say decrease, right? Um, only have to be eventually true, right? That means eventually, after some positive integer, then yes, this becomes true. And the reason is this. So this series that goes from 1 to infinity, right? It yeah, so let's say it looks like this. Well, I can split this up, right? I can split this up and I can say, well, I can go from, let's say, k equals 1 to, let's say, a big N, right? And then add on the rest of the terms, then going from big N to infinity. Kind of like how you can split up an integral into the sum of two integrals, but whereas you integrate from a to b and then b to c, kind of the same property here, right? But the thing is, no matter how big my big N is, this part is always finite, right? This is always finite because, again, it's a positive integer. It might be big, but this is a finite sum. So this will always converge, right? If you're adding up a finite set of numbers, it will always be a number at the end. So this will always converge. So if, for instance, the function in your series, if it's not always positive, so in other words, maybe it does something like this, and I'll just dot some points. So maybe it does this early on. Maybe it's even negative early on, right? And then eventually it starts to do this, and then it never stops doing that. So if for instance I say that this now is my big N, then all these values here, all these values that I have to add up, the function values, then I can just add them up. Whether they go up and down or whether they're positive or negative, it's fine. I can add these up. And then if now my properties of positivity, continuity, and decrease, if those kick in after that, then I just focus on this part and see if let's say I'm comparing it to an integral. So then I would compare this to the integral going from n to infinity, and I would see if that converges, right? So I just wanted to mention this because even though you see it stated every time you see like the integral test stated, which I still haven't stated yet, but I will in a second, and they say positive, continuous, and decreasing. It really, these properties only need to hold eventually, and it could be eventually could be a very, very long time, right? I just wanted to mention that. But let's finally go ahead and state what the the integral test says, and then as usual we'll do a couple examples. So here's our theorem, and this is our integral test. Right, so I will state it, right, just to be to not ruffle any feathers. I will state the theorem in its formal glory. So if let's see, yeah. So if f of x is continuous, positive, and decreasing on the interval. And what I'll do, I'll state the interval just a little bit more generally. Let's say the interval c to infinity, right? And that the function value, right? So those function values coincide with the values in my series, right? So the values of the function coincide with the terms of the sequence. So then, and here is the first conclusion. So if the integral now from c to infinity of my function, if this improper integral converges, so if this converges, then the series from k going from c to infinity of a sub k, that also converges. Right? Again, if there's a finite area under our function, under all these hypotheses, then there has to be a finite area under the corresponding rectangles. And similarly, if the improper integral diverges, then our series also diverges. So they're joined at the hip, these two, right? And all we can say, if the integral is known to converge to a number, the most we can say is that the infinite series converges to something approximately equal to that number, right? So again, if you can't conclude that if this converges to a number, then the series converges to the same number. That is not true. All right? So let's take a look at some examples of this. Now, so when do you use the integral test? Well, you use the integral test when the terms of the series look like something that we know how to integrate, right? Well, what do those look like? Well, you would know, right? You know the types of functions that we've integrated, and we have lots of examples. And I think you also would probably recognize functions that you've never integrated, so you can sort of rule those out. You know, if you have to decide which test to apply, and you're thinking possibly about using an integral, well, make sure it's a function that at least looks like something that we've integrated up to this point. So let's take a look at this. Actually, let me just for emphasis, and let's say this series goes from k to infinity, and it's 1 over k times the natural log of k. All right. And yeah, so let's see if we can we can determine the convergence of this by comparing it to the corresponding improper integral. Right? So this is what we're going to consider. The integral from 2 to infinity. And now when we're integrating, I think the majority of the integrals that we've done were in terms of x. So if you know, just for your comfort level, it's like your safety blanket, you always want to go back to x. You can go back to x like that. So we're going to consider this integral. and we're going to apply our two-step process for evaluating an improper integral. So we're going to first do our area function. So from 2 to b, and then we have the 1 over x times the natural log of x dx. And then the question is, what do I do to integrate this? So now, see, the thing with the integral is we've established several techniques, right? And I think based on the 1 over x and the ln, I think a u sub would work here. So let's try a u sub. Let's try to make the u be the natural log of x, because that will take care of the 1 over x dx. So then my du is 1 over x dx, right? And we have a definite integral, so we're going to switch the limits of integration, right? And because the upper limit is symbolic, even when we switch the limits, the new upper limit will also be symbolic. So when x is equal to 2, u is the natural log of 2. And when x is equal to b, u is the natural log of b. Right? So let's convert this integral over to an integral in terms of u. So my limits are now the natural log of 2 to the natural log of b, and then my integrand is just now 1 over u, because the u goes there in the denominator, and then the dx, you could say the dx over x is just your du, right? So we end up with 1 over u du. And then on my, as long as b is going to infinity, and that's where it is headed, right? It's going to go there pretty soon. And we know that this function, everything here is nice and continuous, and the antiderivative of 1 over u is the natural log of u. And then we have our fundamental theorem, so we're going to evaluate it at this. So there's lots of ln's here, right? So we're going to plug in the ln of b for the u, so we're going to have the natural log of the natural log of b, and then we'll minus the natural log of the natural log of 2. Right? So that is our area function, right? And we could actually write this, we have two terms here. We could write it as a single term by saying the natural log of, and then use that property of logarithms where you'll take the log of this divided by the log of this. So the log of b divided by the natural log of 2. All right, okay, so there's our area function. Now we're going to ask ourselves, well, what happens to this area as the upper limit gets really, really large? So now we're going to take the limit as b goes to infinity of this thingamajig. Right? So the natural log of the natural log of b divided by the natural log of 2. And then ask ourselves, well, what happens to the natural log as b gets very, very large? Well, we know it's a function that grows very slowly, but it gets there, right? So technically, this is the log of infinity over the log of 2, but that's just infinity. So the log of infinity is infinity. So in a nutshell, this is what we have, right? So again, this approaches infinity. So therefore, our improper integral diverges, right? So therefore, let's say it all in one sentence. So since our improper integral, so the integral from 2 to infinity of x natural log of x dx diverges, which it means that there is a infinite amount of area under this curve over this infinite interval. So let's say infinite area. Then the same has to be true for our infinite series. So then the sum k going from 2 to infinity of 1 over k natural log of k also diverges. And that means there is now an infinite area under those rectangles as well. So again, infinite area, right? So that one diverges. Let's do another example. Let's take a look at number 2. Let's try a slightly different function. We just did a natural log function. Well, let's kind of balance it out, the yin and the yang. Let's go with an exponential function. So let's say this one starts at 0, goes to infinity, and then it's k times e to the negative k squared. Right? Let's see if we can determine the convergence or divergence of this infinite series. And again, this does look like a function that we can integrate. In fact, if you look closely, we can use the same technique that we used for our first example, because a u sub will work. So I'm going to compare it to this improper integral. Again, we're not saying that they're equal because they are not. Well, actually, yeah, let's leave it in terms of k. I'm just realizing that I didn't switch back to our trusty friend x, but we can integrate with respect to k. That's fine. So I'm going to make my u. Well, before we do that, let's write down our area function. So the integral from 0 to b of k e to the negative k squared dk, like Donkey Kong. So then we're going to let u be equal to negative k squared. So I'm just going to make the entire exponent by my u. Therefore, du is negative 2k times dk. So in this case, I don't have a negative 2 in the problem like I do in the differential. And of course, we have a way of handling that. So we're going to divide both sides by negative 2. And now the differentials match up. So our k differential is equal to this u differential. And then again, we'll switch our limits. Let's switch our limits of integration and say when k is equal to 0, u is equal to 0. Not much of a switch there. And when k is equal to b, then again we get it symbolic. So it will be u. Maybe let me see if I can scroll a little bit more over. There we go. So u will be equal to negative b squared. All right, so let's convert our integral over to 1 in terms of u. So let's see what we get. So our integral grows now from 0 to negative b squared. And then I have the e to the u. And then I have the negative 1/2 du. Now, it's a good reminder. We probably haven't used some of these properties recently, but let me take out the negative 1/2. So let's take that one out. And then we have the integral from 0 to the negative b squared of e to the u du. Now remember that property that if you change if you switch the limits of integration, then you have to put a negative in front of the integral sign. Well, if we switch these, then we get to change that negative 1/2 to a positive 1/2. So let's go ahead and do that. Just it gets rid of that negative sign, so we have one less negative sign to worry about. And then it looks like this, and then we have our e to the u du. That step wasn't a necessity, but it in some instances it can end up being a convenience and one worth having. So we have 1/2 e to the u, and then our limits now are 0 and negative b squared. So we have our 1/2. At our upper limit, we have e to the 0, which is 1. And then at the lower limit, we'll have the e to the negative b squared. Now, what I'm going to do and I've done this a lot, right? When we have those negative exponents, I think it does help if you apply that property of exponents and just take the reciprocal. So again, just one additional step to reduce the number of negative signs that we have in the problem, right? So this ends up being e to the b squared in the denominator. So that's our area function. Now we take the limit as b goes to infinity of our area function and see what happens. Right? Well, as b gets very, very large, this denominator gets very, very large. So what kind of form do we have here? What kind of crazy infinity form do we have? Well, not that crazy. It's just that kind of form. It's 1 over something very, very large. And 1 over something that's infinitely large is then infinitely small, i.e., it approaches 0, right? So this thing approaches 1/2 the quantity 1 minus 0. So lo and behold, let's write our sentence now. In fact, I'll say a couple things. So since the integral from 0 to infinity of, I'll write it in terms of k e to the negative k squared dk, since this one converges to 1/2, then the series from 0 to infinity of k e to the negative k squared also converges, right? Moreover, we do not know what value the series converges to. Right, so we don't know, so we don't know the value. Oh. So we don't know the value to which this series converges. The best we can say, and we don't even know how good of an approximation it is, right? And again, there are ways we could determine that, but again, that's beyond the scope of this material. But what we can say is that this is approximately 1/2. So I'll just say this: at best, we can say that our series, like this, is approximately 1/2, right? So there's exactly 1/2 square units of area under this curve over the interval 0 to infinity. There is approximately 1/2 square units of area under those rectangles over the interval 0 to infinity, right? And that's our integral test. It's very useful, and it's useful because we have a lot of integration techniques, right? And depending on the type of function in the series, we ask ourselves, is this something that we know how to integrate? We might not like doing the integral, but at least in principle, we know how to do the integral. And knowledge is power. So, we use that power, but we use it wisely. So hopefully you found that interesting. Another problem where it boils down to an integral. And we'll see what else is on tap. So if you want to find out, I'll see you in the next video.